All right, so let's continue to study this question of a Lie group. So now, when I write down a Lie group, we can now think of several things. Number one, it's a continuous group. It's connected, and this kind of gets linked together. It could also be the connected component of a continuous group, because we now know the connected component that contains the origin is itself a continuous group. Because it's a continuous group, we know that it is a manifold, right, which we'll call of eta dimensions. And we know that it has a function that takes two members of the group, beta and alpha, and returns another member of the group, gamma. And of course, we've already gone through in pretty good depth about how this function can be expressed in terms of coordinates. The reason it can be expressed in terms of coordinates is because it's a manifold. So this is, when I write down a Lie group, I can actually just put a bunch of crosshairs here, and I have this to represent the manifold. The underlying group is just identified with its representation, or not representation, its coordinates in R eta. So I'm only going to use two. Now, one thing that's important is to understand that it is pretty conventional, almost universally so, that there's one important spot in R eta, and that's the origin. And the origin in our little two-dimensional example here has 0, 0. When I say two-dimensional example, I'm saying I'm only writing down two of the axes of Rn because of the fact that we're doing this on a whiteboard. We also have the example we've been working that has to do with the shifts and scale, rescaling and shifting, the scaling and shifting of a single point in a one-dimensional vector space, right? So the coordinates, we're talking about scaling and shifting the coordinates of a single point in a one-dimensional vector space. That's the example we've used. But this stuff here, we're talking in much broader generality. But it is true that this point in the manifold, this origin point, is special. The coordinates of some member of the underlying group, which I'll draw here as a box labeled X, right? There's some point in the underlying group that maps to the origin. And we want that point, of course, to be the most significant, or significant, I guess that's an arbitrary term, but the most identifiable point, which is the identity. So the identity lives in this group, that is the Lie group, and that identity maps to a coordinate 0, 0 in the, through the fact that this group is a manifold. Now notice that is not how things worked in our scaling and shifting example. In that case, the identity mapped to this point, 1, 0. So our parameterization of our scaling and shift of the one-dimensional coordinate, that does not comply with what we really would like. We would like that to map that identity point to 0, 0. Now, let's have a look at that, right? So let's consider our example group, right? Let's consider the scaling and shifts. We defined a group element with two numbers, and this defines the group element inside the actual group itself, right? Every member of the group itself can be defined by two parameters. One was the shift parameter, which we called alpha 1, and the scale parameter was alpha 1, and the shift parameter was alpha 2. And we kind of put those in as an ordered pair, and that defined a point here. And it just so happened we took the most naive map possible, the map psi that takes members of this group and places them inside a coordinate system, inside a Euclidean coordinate system. We said psi of alpha 1, alpha 2 comes back with the coordinates alpha 1, alpha 2. We made it that simple. So obviously that's not going to do, because that puts the origin in the wrong place. So we need to now change that. So I'm going to rearrange this a little bit. Instead of calling these guys alpha 1 and alpha 2, I'm going to call the shift, I'm going to call, it's going to be scale and shift, right? I'm going to just write the full words. Every point in here is going to be labeled with a scale and with a shift. And psi, and that scale and shift, I guess we'll have to give it two numbers. I got to come up with some symbols for these numbers that aren't going to cause confusion later on. So let's say the scale is SC, and the shift, see, that's confusing. That's no good either. The scaling will be S, and the shifting will be D, right? So every point in the group is given an S and D, and we know that S has got to be greater than 0, right? So now we're going to take psi of S and D, and we have to return coordinates in R2. And the coordinates we're going to return are, let's see, I better erase this. The rule for this is going to be, we're going to take the log of S and then just D, right? And now we actually will end up with the correct mapping. Because if I take a scale, a value of S equaling 1, which is what the identity would do, well, the log of 1 is 0. So the first coordinate ends up being 0, and D just goes to D. So if the shift is 0, the second coordinate goes to 0. So now the identity element gets mapped to 0, 0. And if I want a very, very small shift, say S was, 0.001 or something, a very, very small scaling. I want to shrink the coordinate to 0.001, and I want to shift by, say, 3. Well, that's going to be e to the log of 0.001, comma, 3. And e to the log of 0.001, by the way, is going to be a negative number, right? What am I doing? I'm not doing e to the log, right? I'm just doing log. Sorry. It goes to log of 0.001. So it ends up, this point, this scale and shift gets plotted to a negative number for the x-axis somewhere, and then 3, right? It'll be at 3 and at log minus 0.001, right? So this solves that problem, but we've now got a more complicated mapping psi. It used to be, our original mapping was we just took the scale, took the shift, and plotted it. So the psi mapping was the identity mapping. Now we've made it a little more complicated. The psi mapping is actually the log of the shift, and that would be sort of the psi 1 is going to be the log of the shift, and psi 2 is just going to be equal to, psi 1 is the log of the scaling, and psi 2 is just simply the shift. How does this affect the transformation function f of some group element alpha acting on a coordinate x, right? Well, now I have to take, so if I'm dealing with the group element that has a shift of s and, a scaling of f and a shift of d, that has coordinate log s d, right? And f acting on this is going to be, so this is the coordinates. Now I replace this with the coordinates of alpha. So alpha's first coordinate and alpha's second coordinate and x. Now it used to be this first coordinate was just the scaling and the second coordinate was just the shift, but that's not true anymore, right? But now what I do is the result is going to be e to the alpha 1 x plus alpha 2. And that's the new transformation function, right? The function that's from the Cartesian product of the group and the underlying vector space or the carrier space back into the vector space. So, and then the question is, well, how does it affect the composition function? That's actually probably even more important. I should have probably done this one first. So if I'm doing a composition of beta and alpha, I want to say, well, I can write this down as the coordinates of beta, which will be beta 1, beta 2, alpha 1, and alpha 2. And now, it used to be, the answer was just beta 1, alpha 1, and beta 1, alpha 2 plus beta 2, right? That was what the answer used to be. But not anymore. Now, the answer is going to be, the answer to this is the coordinates of the group product B beta alpha. And that's going to be beta 1 plus alpha 1. And then it's going to be e to the beta 1 times alpha 2 plus beta 2. And then if I take, let's see, the other mapping that's important to know is if I take a group element with coordinates alpha 1 and alpha 2, and I seek its inverse, right? The inverse now is going to be minus alpha 1, then minus e to the minus alpha 1 times alpha 2. And if you take these coordinates and plug them in here, right, what you'll see is that the beta 1 plus alpha 1 becomes minus alpha 1 plus alpha 1, which is 0. And you'll see that minus e to the minus alpha 1 times alpha 2 minus e to the minus alpha 1 times alpha 2. So you get 0 there. So you get 0, 0, which is the coordinates of the identity. So this is how the inverse is done. So what we've done here is we've done a reparameterization of our group. And from now on, that's the parameterization we're probably going to be using, because it has this very important property that 0, 0 is the identity. And the reason that's important is we're going to do a lot of Taylor expansions around the identity, and this allows us to do things in terms of Maclaurin series around 0, which is a lot easier than any other way. So when we use this group for an example, we are going to use this parameterization from now on. But this is a good exercise because we're going to actually do some examples later on where we do different representations of different groups, and we're going to reparameterize things all the time. And just getting familiar with that, this is the first sort of stop along the way. All right, so there's another thing about this I want to discuss. I want to imagine the origin of the coordinate system that is capturing our Lie group, our eta, and then imagine a neighborhood around it. Now, we know that the inverse map is continuous, which means that generally what this means is if I take a point and I find a neighborhood around it, and then I find the inverse of that point, and I take a neighborhood around it, the inverse of all these points in the neighborhood are going to land inside a neighborhood around the inverse of the original point. So if that's the inverse map, right, I know that the inverse of the points inside this neighborhood will land in this neighborhood. Now, when you look at the origin around, we know that the and now this is all in coordinates, right? So I'm identifying every point in Rn with its group element through its coordinates, which I can do because it's a manifold. So if you look at this neighborhood, the inverse of the identity is the identity itself. So the inverse of everything near the identity must be near the identity, right? So that's kind of important, that the inverse of all of these points is actually inside a neighborhood of the identity. So you don't have the inverse of points that are within a neighborhood of the identity in some other place in the manifold. So that's one important point. And now we come to an application of our notion of analyticity. Let's look at phi of the group function alpha beta. Sometimes I write beta alpha, sometimes alpha beta. So this has got to be analytic, which means that it equals its Taylor series. So what is the Taylor series of this thing? Well, the first term of the Taylor series, we're going to do this as a Taylor series around 0. So the first expression will be the coordinates of 0, and 0, right? And then to that we will add alpha times phi, the derivative of phi with respect to this first coordinate position, or the first slot. So we'll call the general function phi x, y. So it'll be phi as the derivative of phi with respect to x. And it will be multiplied times beta of the derivative of the second slot, which we'll call phi y, right? So that is the first order term of the Taylor series. The second order term, we don't need to worry about it because we're going to ignore it, but in principle, that second order term will be alpha squared phi xx plus beta squared phi yy plus alpha beta phi xy, and I think everything will be over a 1/2, and I think there might be a 2 here. Yeah, I'm pretty sure there's a 2 here, so there should be a 2 here. But it doesn't matter because these are all second order, right? So what we're interested in, of course, is when alpha and beta are small coordinate differences away from the identity. So the identity is at 0, 0. So the alpha element is going to be, say, here, and its coordinates will be delta alpha 1 and delta alpha 2. And the beta element likewise will be here with delta beta 1 and delta beta 2. And they'll be small because they're small from their coordinates of these group elements are small relative to displacements from the identity. So because small means essentially that delta alpha 1 squared is just so small you can ignore. So we ignore all of this stuff and all of the higher order terms, and we're left with this nice linearized version of things. So what I'll do is I will just emphasize that we're dealing with something small. I'll put a delta there and a delta there. And right now, this, for example, is only in one variable. So I guess the way I really should write this is something like phi delta alpha 1, 0, comma, delta beta 1, 0, something like that. Or why bother? Why be afraid? Delta alpha 2, delta beta 1, delta beta 2. This has now got 4 variables, so big deal. So I just write this equals phi 0, 0, 0, 0. Right? This is more akin to what we're doing here, right? We have 4 different coordinates, one for the first group element, one for the second. So this will be plus delta alpha 1 of phi with respect to the first slot. So now we have to name these slots. So we'll name it x, y, w, z. So dx plus delta alpha 2 phi y plus delta beta 1 phi w plus delta beta 2 phi z, right? And then higher order terms. So this is the linearization. This here is the linearization of literally our situation here where we've actually sort of set eta to be 2, right? So now the reason so we know we can do this because a Lie group is analytic, and it's analytic, that means it equals its Taylor series. And because it equals its Taylor series, we know that if we can write the Taylor series with small enough displacements, we can ignore the higher order terms and the limits that this displacements get smaller and smaller, which is the same thing as saying the coordinates of the group elements we're considering are getting close to the coordinates of the identity, and the coordinates of the identity have been set to 0, 0. So now you kind of see why it's important to set the coordinates of the identity to 0, 0. So now what I'm trying to get at is I want to consider, consider this, right? Consider what we've written right here. Say we want beta to be the inverse of alpha, right? We want beta or delta beta to equal delta alpha inverse. Well, if that was true, then this formula would be true by replacing these guys with those guys, right? Which means it would have to equal phi 0, 0, 0, 0 again, plus delta beta 1 phi x, right? The phi x stays the same because now delta beta 1 is being put in the first slot. We're naming the first slot the x slot. Plus delta beta 2 phi y, plus, let me erase this because I'm going to run into it, plus delta alpha 1 phi w, plus delta alpha 2 phi z. So using the fact that inverses commute with each other, right, I'm saying that this expression is going to equal, that this expression here has to equal this expression here. And if they're equal, then if their differences should cancel to 0. So, so if I subtract this term from this term, the 0, 0 guys will cancel out right away, right? Right, those guys will cancel. And then I'll be left with, let me just collect the terms. And after the subtraction, I think this is what you get. You get phi x minus phi w times delta alpha 1, phi y minus phi z times delta alpha 2, and phi w minus phi x, which is, note the reverse of this, delta beta 1, and phi z minus phi y, delta beta 2. So this has to be 0 if beta is the inverse of alpha. So the only way that can be true is in the unlikely circumstance that these phi x and phi w's cancel to 0, which can't really be because this is true essentially for, we want this to be true for any group operation, right? And it's not likely that those derivatives are all going to cancel nicely. But it is true in the circumstance where delta beta 1 equals minus delta alpha 1 and delta beta 2 equals minus delta alpha 2. And that's, so all of this is to say that the inverse delta alpha mu, a group element that has the coordinates delta alpha mu, where mu now represents 1 and 2, the inverse of this group element is minus delta alpha mu, right? That's how that works. And it works because of the fact that inverse operations commute, and we can analytically expand this because it's a Lie group. And a Lie group says that this function, not only is it continuous, but it's analytic. And therefore, the inverse of an infinitesimal, the inverse of a group element that is who has coordinates infinitesimally close to the coordinates of the identity is just the group element with the opposite coordinates, right? So that'll be a useful fact. Gilmore just sort of stipulates it, but I'm kind of fleshing it out a little bit.
All right, so in this lecture, what we had done, to summarize, is we reparameterized the basic elementary Lie group. We demonstrated a reparameterization whose goal was to make sure that the identity element of the Lie group had coordinates 0, 0. Like before we had coordinates 1, 0, now we have coordinates 0, 0. And that will be something we will stick with almost forever within this study, is getting that point across, that we really want the coordinates at 0, 0. And we showed how the parameterization affected the two fundamental functions that we have to deal with. Probably this is the most fundamental function, right? The function of the group operation. And we showed how that reparameterization brought us to this additive form of that function, because we used this, essentially we used a logarithm, and so a product became an addition, and then we have, of course, the exponentiation slips in there. By the way, this reparameterization can be expressed in the matrix form too, right? The matrix operation, or the two-dimensional representation we talked about last time, is also modified by this reparameterization. We'll talk about that a little later. And then also the reparameterization affected the form of the transformation function, where you have the group operation and the element of the underlying a geometric space, or the vector space, and that transformation, which takes the coordinates of the group operation, which are now centered at 0, 0 for the identity, and an element of the vector space, this is the new transformation. So we talked about the reparameterization, and then I went through this sort of demonstration for two purposes here. The key purpose was to show this fact, that the coordinates of a group element with coordinates infinitesimally close to the identity, its inverse is just the group element corresponding to the point with the opposite coordinates, right? But this was also an introduction to the idea that this group operation was analytic, and we were able to use the Taylor series to expand it. Okay, so this is a shorter lecture than most, but the next lecture is going to be a deep dive into this analyticity and understanding the notion of the generators of a Lie group.